logistic equation. Last time before the exams, we had done the law of exponential change. You can still be able to go through that. So basically, the logistic equation is a better form. Basically, that is what the literature is noting there. Better form more than the law of exponential change because it has a carrying capacity. Remember last time the law of exponential change, it was just given by, I think you are using P naught, or you can use capital A and then exponential RT, where R was the growth parameter. So the law of exponential change has only one thing, which is just the growth parameter. But when you come to the law of the logistic equation, it is a bit different, basically, because now on the logistic equation, you can be able to see it has another parameter, which is what? Which is R. It has another parameter, which is R. It has R, and it has what? K. Where R, this one still is the growth parameter, but K now is the carrying capacity. Basically, the carrying capacity is how much the resources can be able to accommodate a population. So if you go to a classroom, basically a classroom is made up of basically can be able to hold 50 students. If we have more than 60 students, then we say that that class cannot be able to hold 60 students. If you go to a vehicle, a five-seater vehicle, you'll expect to see 5 people. But if we are 10 of you cannot be able to say that you can still be able to go into the vehicle. So the carrying capacity of the vehicle can only accommodate 5. So basically the resources that are around, there is the carrying capacity that are there that you can only can be able just to carry. So the logistic equation basically the indifferential form is given by this one here. You can be able to see it there. dp over dt rp1 minus pk. So that is the differential equation that gives basically the logistic equation. That is the equation. You must remember it. If you want to do any equation of this one, you must be able to remember it, just like the law of exponential change. So from there, you can be able to see that now the author of this document was able to come up, was able to integrate that dp over dt rp 1 minus pk to get this equation. I'll not go to the integration because you guys have not learned integration by parts, oh sorry, by partial fraction. It is a lengthy one. So the equation that I want you to remember is this one here, one that I'm circling. So that equation there is the most important one. That pt, basically the solution for the logistic differential equation is given by that. pt is equals to p naught k, p naught plus k minus p naught exponential rt. So there are two equations. So the first one is here, the one that I've, let me circle this one here. You must be able to remember it, the differential equation. From the differential equations, remember what you are doing when I was introducing to you integration. When you had dy over dx or dy over dt, we were integrating to get y. So they are basically integrating to get p. So these are the two equations that are very, very important. Very, very important if you want to do any equation on the law of what? Sorry, on the logistic equation. So the first one is easy. dp over dt rp brackets 1 minus p over k, where p is the population at any time and k basically is the carrying capacity and r. The second equation that you are seeing here, it is p naught k, where the p naught is the initial population. Basically the population at time is equals to 0. So it's given by all that k minus p naught exponential rt. So I think we can be able to do this example here just for me to do what, to explain. Example number 1, a population of bacteria grows according to the differential equation, that one. When t is equals to 0, the population is 200 g. Find the population p at any time. So this one, you have been given what? The differential equation. This one is the differential equation that you have been given. That one. That is the differential equation that you have been given. Now, and then you have been given when t is equals to 0, the population is 200. So here, let me move away from the pens. At least I can easily be able to explain. So we have been given that. We shall compare with the solution later. Let me write here. So that is the equation that we have been given. So the equation that we want basically is the population at any time. The equation that I had told you, you must be able to remember. Remember that equation? What we want is this equation here. P it was given by PT. It's very thin. PT was given by P naught K. P naught K all over P naught plus K minus P naught, and then you multiply by negative what? RT. The R is the gross parameter, K is the carrying capacity. So you have been given this equation here. This is what we want. And if you want to do this one, first of all, we need to get the value of K, we need to get the value of P naught, and we need to get the value of what? Of R. How do we get that? We compare now. The equation that we have been given here is this one, dP by dt is given by 0.03 P, and then 1 minus P all over 2000. All over 2000. dP over dt is equal to 0.0. That's the equation that is there. So I want us to compare with what the other equation, the differential equation. We pick out some term. The differential equation that I told you to remember was given by this one, Rp all over 1 minus P all over K. I want us to compare the two equations on the what? On the what? On the right hand side, basically. So this one that you have been given. So it's a matter of comparison. If you remember the equations, then we shall just get the values of K, the value of R, and we put it basically on PT. So I want us to compare these two, comparing these two to see what we shall be able to get. So I'm comparing. So you can be able to see that the dP and the dt, they are corresponding. So the P and the P, it is corresponding. So it means that our R has to be what? 0.03. Then here, the one and the one is corresponding. So it means our K has to be the same as what? 2000. So you just have to pick the terms. If you remember the equation, it is easy as that. You just have to pick the terms. So with direct correspondence, we are seeing that our R, growth parameter, is what? Is 0.03. And our K is what? 2000. That is just the right correspondence. So now all these values, we shall now input it basically to this equation, and we are done with the solution. But again, from the question, there's something that we have been told. When T is equals to 0, the population is 200 grams from the question. So this one here, let me circle it in what? In green, that one there. So we have been given the value of P naught. So that is the value of P naught. So even the value of P naught is known. Our P naught is what? From the question, our P naught is 200 grams. So our main task now, we have been told to find the population P at any time. So we input all the values at PT, and we are done. So PT now will be given by, so the values that are there. So P naught is known. So P naught is 200. And then times our K, we have gotten it as 2000. And then our P naught again is known, which is 2000. And then our K is still, no, our is not 2000, but 2 is what? It is 200, sorry. So our what? Our K is known, which is 2000, and then minus 200. The whole of this one we multiply by exponential negative. Our R is known, 0.03, and our T is unknown because they are telling us at any particular time. So what I did, first of all, I remembered the equation for the differential equation. Then I did a direct correspondence. Then I picked the values, and then I just replaced them basically on the PT. And if you check my solution and what they have here, is the same. You can be able to see they're multiplying 200 times 2000, 200 plus that one, and the final solution is that. So you remember the two formulas, and then you do a direct correspondence, you'll be okay. But if you don't remember the two formulas, it becomes a bit hard for you to be able to do it. So this is the differential equation that have been given. So I'm being tasked to get the value of now the population at any time, which is PT. So you have said, first of all, what we normally do, we shall first of all do a direct correspondence. And you have said that you must be able to remember, uh, the equation, the differential equation, and the PT. So because I've been given the differential equation, let me first of all do a direct correspondence. So what I've been given here is this one, dP over dt is equals to 0.05 p. I'm just repeating the equation that I've been given, 1 minus 0.001 p. Now, the one that I said we remember was this equation, the differential equation for the logistic. It was given by R, P, and then 1 minus P all over K. So I'll do a direct correspondence now. I do a direct correspondence. So the dP and the dt, they are going together, no problem. I think the R is easy to see. The P and the P, they are going together. So the R here will be what? The R growth parameter will be 0.05. The one and the one, they are going. I have another P here. Can someone try to give me the value of K? If you do the direct correspondence, can someone try to give me the value of K? And yes, remember the growth parameter can never be a decimal. Sorry, the carrying capacity K can never be a decimal. It has to be a value greater than one. So if you do a direct correspondence, check this one out. P over K is the same as 0.01 P. So the P and the P, they are cancelling. You can be able to see they are cancelling. So what I'll do, I can be able to, so I'm getting 1 over K is equals to 0.01, sorry, 0.01. So if I find the value of K, the only thing I can be able to do is to get the reciprocal both sides. The reciprocal of 1 over K is K, and the reciprocal of this one is 1 all over 0.001, which you shall be able to get as a what? 1,000. Easy as that. So K is equals to 1,000. Let me go back now to the question for me and get the value of P naught. So P naught is the population at T is equals to 0. So let's get our value of P naught, which is given as 300. So now I'm on the final stretch. Find the population P at any time. So I recall the equation for the population at any time. It was given by this one. It was given by P naught K all over. You must be able to remember this equation if you want to do it. P naught plus K minus P naught, and then exponential negative RT. So our P naught was 300. Our K, we have gotten it as 1,000. And then our P naught is still 300. And then our K is 1000 minus our P naught is 300, and then exponential negative. Will it fit here? 0.05 t. My spacing is not, but it is negative 0.05. Let's go and confirm our answer, what they have done. So we have multiplied 300 times 1000. You can be able to see we have 3000 times 1000. Basically, it is here 3000 times 1000. Then you have 300, which was our P naught. Then we had 1000 minus 300, and then exponential negative that. And then you just multiply the two, and you get the final answer. Now, here, this one here, let me show you what they have done here. Now, to get this final answer, this one is in simplified form. This one here, the final answer here, this one is in simplified form. So what have they done to get the simplified form? Because the values are so huge, what have they done? They have used a principle that in maths that they call it what? They call it, we call it what? Here, the final answer here. Check the final answer they have gotten. They have used factorization to be able to simplify this one here. Factorization. Basically, we have 300 and 700, and we have, so here, the GCD, the number that we can easily factorize is what? Is 100. So if you factorize here and 100, you remain with 100, and then you remain with the three, how many zeros? You remain with only 3 zeros, and then here, you can still be able to factorize 100 outside, then you remain with 3 plus 7 exponential negative 0.5t, and then you cancel that one and that one. So that's what they are getting. You can be able to simplify if you prefer, so that at least you don't have so many big numbers. You can still be able to do that. You can still be able to do that, to be able just to simplify if you prefer. So do a direct correspondence, and then it is easy as that. So let's move to another question we see. So another question, the population of bacteria grows logistically. Suppose the initial population is 3 milligrams of bacteria. The carrying capacity they're giving us as 100, and the growth parameter is 0.02. Find the differential equation satisfying the population. So let me remove the solution first of all. Go home, remove the solution, and then we shall be able to compare. So, or we do one at a time. Then let me control. We do one at a time. So you can be able to do the first one. So we do one. So find the differential equation satisfying that. So the differential equation, you have to remember it. We know how it looks like, and then we input everything. So the differential equation is given by this. It was given by dp. dp all over dt was given by rp, and then 1 minus p all over k. So from the equation, our r, the growth parameter is 0.2. Our k, the carrying capacity is what? 100. And basically our p naught, which we shall use later in the other question, our p naught is what? Is 3. It's only 3 bacteria. So we just input everything. Our R is 0.2 P 1 minus P all over our K, which is 100. And we are done with that one. So that is the differential equation. If you remember the differential equation, then you're okay. If you forget the differential equation, the formula, you'll not be able to get it. So let's check the answer. So it's the same answer. So check this one out, the final answer. You're getting that one. Remember P prime. P prime means you are differentiated this one in terms of T. So when you see P prime, it means dP over dt. Or you can use P prime. So we have 0.2. Then what they have done, they have divided 1 divided by 100. That's why they are getting 0.01, but it is still the same thing. It's still the same thing that we had. The second thing, we get the what? The population at all times. So the population at all times, again, we shall again go back to the formula, the population at any time. The population at PT is given by PT. This one was given by P naught K, all over P naught, plus K minus P naught, and then exponential negative RT. So our P naught already, we have been given those values. Our P naught is 3. Our P naught is 3. And then we multiply by our K, which is 100. And then our P naught is still 3. And then we have K minus P naught, 100 minus 3. And then exponential negative. Our R, our growth parameter is 0.2. And then our T. So if you check, let's confirm our answer, what they got. So you can easily be able to see. There's a mistake here. Basically, the power has gone down, but it is still okay. So this is the final answer they are getting. And you can be able to see it's the same. 300, ours you are getting 3 times 100 is 300. Then we have 3, 100 minus 3, that is 97. And then exponential, there's something that has gone down. This one is supposed to come back here on the power. It's supposed to come there. So remember there's a negative 0.2t. And then you are done. So we go to the next question. The next question is asking, this one is wrong, it's supposed to be 20. So they're asking, when will the population reach 20 milligrams? So first of all, you ask yourself, what are they asking, first of all? What are they asking? You have to be able to understand the question. If you don't understand the question, then you cannot be able to do it. So what are they asking? That's the first. When will the population reach 20 milligrams? So they are dealing with the population. And the only equation that will give you the population is which one? This one that we have formed here. The equation that we have formed here is the one that is for population. The other one was for the differential equation. So we shall be able to use that one. So they are asking, when will the population reach 20 milligrams? So they are asking for the what? For the time. For the time when the population will reach that. So now what we have been given as 20 milligrams, this one is our what? Is our PT. So we shall be able to replace it, that one there. And then we solve now for the value of what? For the value of T. So I'll replace and see what I'm getting. So 20. Then we had 300 here. And then we had here 3 plus 97 exponential negative 0.2t. So we are solving for the value of t because they are asking when. When is for time. Now for this one, we can be able to do a bit of it's called what? Cross multiplication. We see. We can be able to do some cross multiplication. We can bring this side, this one, this side, and then we bring the 20 this side. So check what I'll be able to get. If I do that, I bring the, so I remain with 3 plus 97 exponential negative 0.2t is equals to 300 all over 20. That's the most simplest thing I can be able to do. I bring the denominator up, and then I bring the numerator 20 down to become a denominator. So I can be able to cancel that one and that one. So 30 divided by 2, I'm remaining with what? 15. So I have 97 here. Exponential negative 0.2t. So if I do this one, I remain with what? 15. And then I subtract the 3. I subtract the 3. When a positive number will cross over, it shall become what? Negative. So 15 minus 3, I'm getting that one as what? Negative 0.2t. 15 minus 3, I'm getting that one as 12. So I remove this 97 by dividing here by 97, and I divide here by 97. I'm still continuing. So If I divide 12 divided by that one, let me see an approximate what I'm getting, 97. So I'm getting exponential, I'm getting exponential negative 0.2t. I'm getting something close to this one, 0.1237. Okay. So how do we solve for t now when we reach there? So that is the biggest question. I want to see if someone can be able to remember. Bring the t down, we use logarithm. I think I explained this one in the previous example. So we introduce ln both sides because ln and exponential, they have a relationship. And you can be able to get it with your calculator, you'll be able to see. So I'll introduce ln both sides. That is true. So let me introduce ln both sides. Ln, so I'll have here ln exponential negative 0.2t is equals to what? Ln 0.1237. So when you have ln and exponential, what will happen? In the previous example, I said when you have ln and exponential, basically you'll just remain with the power. You'll just remain with the power. So on the left hand side, we shall just remain with the power. We just remain with the power on the left hand side because the ln and exponential, the if they are cancelling. So you'll just remain with the power. So negative 0.2t. Now ln 0.123, when I use my calculator, let me see, 0.1237. I use that one, I'm getting negative 2.08. Is it 99? Let me 99. I'm getting that value using a calc. So t is easy now. T will be given by negative 2.0899. I divided this one by negative 0.2. And the value of t divided by 0.2. I'm getting approximately t will be the same as 10 points. 10 points, almost 5. We can work with 10.5. 10.5. That is the value of t will be given by that. And it's always in hours. It will always be in hours, not in seconds, but in hours. So if you have been given that one and you have been told the time when, remember somewhere you'll have to introduce the what? You'll have to introduce the ln to bring it down. Just do some manipulation, and the equation that we are using is the one for pt. So you replace where the 20, where we have p, you replace with 20, do a bit of manipulation, and you'll be able to get the value of t. Let's see what their answer was, what they were getting. Now part C. But see, let's see what they were getting. They were getting 10.45. I think we have rounded off. In my calc, oh yes, sorry. In the calc, it's supposed to be 10.45. The value here. Sorry for that. Because in the calc, I was getting 10.449. So my answer is a bit off because I think I rounded off a bit early, but it is almost the same. So this one is supposed to be 10.45. If you do it, you can confirm the answer, 10.45. You'll be able to get that one. So the next question they are asking now, part D, when will the population reach 200 grams? So you can still be able to do this one. This one is easy. It is almost times 10 of this one, times 10 of what we have done here. So instead of having 20, you'll have here what, 2,000. That one you can easily go back to the notes and you can easily be able to do it. So for 200, the equation that we'll be solving now will be this one. But I don't want to do that one, part D. I don't want to do part D, this one, because it's a matter of replacing, and you can easily be able to follow what we have done. So we'll just have to do the 200 on the left hand side. You solve this equation. 200 is equals to 300 all over, let me confirm the equation. was 300, 3 plus 97. 3 plus 97, and then exponential negative 0.2t. So if you follow the same procedure, the value that they were getting, you bring the 200 on this side, and then you bring that other on that other side. The value that they were getting, let me confirm here, part D, they were getting, they are getting which value? They're getting a negative value, but this is meaningless. There's no such t since. So, and you can be able to see the conclusion. The value they are getting is a undefined answer. Basically, there's no there's no log of a negative number. So they are saying now the population will never reach. So if you get an undefined answer, you are sure that the population will never reach that value. It will never be able to reach that value. So that's the conclusion that they have been able to make. You can still be able to follow that example. No need. This one is very important for me. This part here, the limit here. You have not done limits, but I can just introduce some limits. So the growth parameter. This equation, if you remember, this one is the equation for PT. This one is the equation for PT. So given PT, you can directly be able to calculate the value of K, the growth parameter, this one, sorry, the carrying capacity. You can easily be able to do this one. By doing what? By introducing the limit. Limit basically is like the value of T as it approaches infinity of now basically your PT. So you just have again to be able to. And what I need you to remember is only on this, that when you have exponential, because you can be able to see the t is only affecting this term here. Let me circle it. It's only affecting the exponential. There's no other place that we have the what? The t. So when you have a exponential negative infinity, this term will always go to zero. If you can be able just to remember that, you have not done limits, but you can be able to remember that when you have pt and as t is going to infinity, this one is used to calculate the value of k. Is used to calculate the value of k. So the only term that will go to zero is only the exponential function. Is only the exponential function that will just go to zero. If you can be able to remember that, you can be able to do any question now. Because sometimes you cannot be given, you will be given PT, and then you're told to calculate the growth constant. We shall be able to do an example. Sorry, the carrying capacity, yes, the growth constant and P naught. And I'm saying for you to be able to calculate K, the carrying capacity, the exponential function is the one that we shall take to infinity. And because we have a negative here, the exponential function is the only one that will go to zero. Will only be able to go to zero. And when you replace zero here, so K will be given by this 550 all over 10 plus 20 times 0. Only the exponential function. When we do this one, we'll get 550 all over 10, because when you multiply the number by 0, you still get 0. So the answer here will be 55. Again, I will repeat, is only the exponential function that will go to 0. I don't want to go to the theory bit, because some people may get lost. I'm making it as simple as possible. Only the exponential function will go to 0 as t is going to infinity. That one is called infinity. And because we have a negative number, we have a negative, it will always go to 0. Maybe I'll ask a question. Is it a bit clear, or it is still a bit, I think I've repeated so many times. Let's do an example to demonstrate this one. This one is the proof. This one is a good one. This one, let me remove this one, and then we shall compare the answers. This is the final I'm doing. So you see now, this one is not a differential equation, but this one is the population at any particular time. Suppose that a particular population of bacteria obeys the logistic formula Pt is equals to T plus 3 exponential negative 3T, where P is the milligrams and T is in hours. Find K, R, and P naught. So let's first of all find K. Let's find the K. So we have said for us to be able to come and find K, we shall find the limit as T is going to infinity. So K we have said will be given by limit as T is going to infinity of our Pt. This one will be given by limit as T is going to infinity of 2000 all over 2 plus 3 exponential negative 0.3t. Now we have said only one term will be affected. So which term will be affected? So you have said only one term will be affected here is only the exponential. So as t goes to infinity, only this term will go to zero, only that term. So when I replace there with 0, this is what I'll be able to get. I'll get 2000 all over 2 plus 3 times 0. Then you'll get 2000 all over 3 times 0, that is what? That is 0, so over 2. When you do this one, what are you getting? I'm getting 1000. And I'm done. So that's how you calculate the K when you have been given PT. When you have been given the differential equation, you do a direct correspondence. Let's find the value of R. R is easy. R is basically the value next to the exponential. You remember the equation? Let me repeat it here. The equation that we had PT, the one I told you to remember, it was given by P naught K all over P naught plus K minus P naught all over negative RT. Now, this one now, for the value of R, you just do a direct correspondence. Check what we have. The R is only on the exponential. So if you do this one here, check this one, compare that one with this one, with the equation that is here. If you compare that one, our R has to be the same as what? 0.3. So our R growth parameter is easy to see, 0.3. 0.3, a direct correspondence. Easy as that. Our R, we just do a direct correspondence. That one has no problem. Now, let's do now for the what? I want to do my P naught here because I want to use this equation. So my P naught is the population at what particular time. We start from there. From the theory, the P naught is population at t is equals to 0. So P naught is a P at what? At t is equals to 0. So I'll just replace the value of t is equals to 0 there. So I'll be able to get P 0 will be given by 2000 all over 2 plus 3 exponential negative 0.3 times 0. If you multiply any number by 0, you get 0. Any number raised to power 0 is the same as 1. So it will remain with 2000 all over 2 plus 3. If you do 2 plus 3, you'll get 5. So 2000 divided by 5, you'll be able to get 400. So milligrams. So that is basically the P naught. It is the population at t is equals to 0. So you just replace the 0. And if you check, basically, that's what they got. You can be able to confirm our answers. The P naught they got was 400 milligrams. You can be able to see we have gotten that one. Our K, they got K as 1000, still the same. And then our R, they just read it at 0.3. 0.3, you just read it. Our R is 0.3. Our R is 0.3. Sorry, here, and it has gone down 0.3. You cancel that one, is 0.3. And you can easily be able to see. So that's how you do it. So the most important thing was how to get the value of K. And you have said for the value of K, We check k will be given by the limit as t is going to infinity, and basically you just have to replace the exponential function with zero. You replace the whole of it with zero, and then you solve for the value of k. Any conclusion for this one? The conclusion is this one. The conclusion number one, you must remember the differential equation. You must be able to remember the differential equation. That's very important. The differential equation, which was given by dp all over dt, was given by rp 1 minus p all over k. That equation number one, you have to remember it if you want to do this one. The second one, it was the population at any time, our p. And this one, pt, was given by p naught, was given by p naught k all over p naught plus k minus p naught. Remember, you always subtract the carrying capacity and then minus negative RT. Now you have said that our p naught is the population at t is equals to 0. Our k is the growth parameter. Sorry, our R is the growth parameter, and our K is the carrying what capacity. The final thing we have said, for us to be able to come and get K, we get the limit as T is going to infinity of PT. And the only thing that will be affected is exponential. Exponential negative RT is the one that will always go to zero. So those are the three things you must be able to remember. Three things, only three things. So the k, you get the limit as t is going to infinity of pt, and the only function that will be affected is only the exponential.